Okay, this is Professor Amoro's Thursday, February 6th differential equation lecture. I'll make a condensed version of today's lecture. We had bad weather, so a few of you missed class. I'll try to explain what we did. There's a worksheet on Brightspace you should be able to do after this lecture. If this lecture, I'll try to go pretty quick, but if it's too slow for you, you could always watch it on extra speed. I think you can increase the speed of a YouTube video by clicking the settings down on the right corner, but hopefully I'll try to keep it from getting too boring or slow. Okay, this is the last lecture. Remember, we have an exam, your second exam, next Thursday. So, next Thursday, that's February 13th. In class, I think, so we can dedicate Monday to review when we have class on Monday. I think Wednesday next week, the class is canceled because of Wellness Day. But that's fine because we should be able to finish the material today, and I'll post some practice problems tomorrow on Friday. And so you'll have almost a whole week to keep reviewing. And of course, you make sure you're doing the web work homework, which are still open. And okay, so let's start talking about today. So let's start with an example, and this will be a good reminder of what we've been doing. Before we do an example, why don't I just remind you what we have been doing? So we're solving these second order linear constant coefficient homogeneous. There's a lot of things to say about these. Let me see if I can write that better. Homogeneous ordinary differential equations. So an example of that would be a constant times y double prime plus another constant times y prime plus a third constant times y equals 0. What makes it homogeneous is the fact that the right-hand side is 0. What makes it linear is that all the y prime term, the y double prime term, the y prime term, and the y term are all in their own separate terms. They're not being multiplied by each other. They're not underneath square root signs or inside logs or cosine functions or anything like that. Okay, and then what makes it constant coefficient are these things in front of the y double prime, y prime, and y are just numbers rather than functions of t or x. And what makes it second order, of course, is that the highest derivative is 2. All right, and then if you remember, the way that we solve these is we create what's called an auxiliary polynomial, which is a times r squared plus b times r plus c equals 0. That comes from this. We solve that and we find the roots. What does it mean to find the roots of a polynomial? It means solve for that polynomial equal to 0. Okay, you might be able to solve that by factoring. Remember, you could always use the quadratic formula, which just says if you're having this equation here, we have 0 on one side, then in the coefficient of r squared is called a, the coefficient of r is called b, the coefficient, by itself, the constant is just called c, including any negative signs possibly that would be included with a, b, and c. And the formula for the roots is, this is just the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. Make sure you remember that. You need to do that once in a while for an exam. So let's do okay, and then remember, typically what we do, if we get two roots from this, r1 and r2, and they're different, and they're real numbers, then I think we know what to do, right? The solution will be the solution to the differential equation written here is y, or y of t, c1e to the r1t plus c2e to the r2t. We've done a number of examples like that. That's when you get two different roots that are real. Okay, we've seen that a number of times. This is the solution to the differential equation you see here. Okay, so And what did we learn last time? Last time, let's do an example to sort of remind us what we had last time. So, switch colors. Something like this. What if I gave you an equation like this? Y double prime plus 7y equals 0. Okay. Now notice this equation is missing a y prime, so that just means that that just means that this term here is missing. That's usually the damping term or the friction term. Nevertheless, let's write out remember the solution method. So here you're being asked to solve this. This would be a good question for the test that we're going to have next week. Something like this. So here's the solution. The first thing we want to do is we want to solve the auxiliary equation, which is, in this case, would be r squared plus 7 equals 0. Why is it 7 and not 7r? The r would go with the y prime term, right? But we don't have a y prime term. We just have a 7y term. So that's, in other words, in this case, a is 1, b is 0, and c is 7 in this setup. Well, if you wanted to, why don't we try using the quadratic formula, even though we don't really have to do it here. Let's use the quadratic formula to solve for these roots. So we have the roots are negative b. Well, in this case, b is just 0, plus or minus the square root of b squared, which is 0 squared, minus 4 times a, which is 1, times c, which is 7, all over 2 times a, and remember a is 1. Let's simplify this. Well, negative 0 is just 0, so that's gone. We just have plus or minus the square root of, I believe this is negative 28, all over 2. Okay. Well, look at this. We have a square root of a negative. You can't have a square root of a negative, or at least you can't write that as a real number. We learned this the other day at the square root of negative 1. We represent that with the imaginary number I. So if you want to do the square root of negative 28, that's just going to be plus or minus the square root of 28 times I over 2. Now I pulled the negative out and written it as an I. You could actually do something. You could leave it like that, but if you like simplifying things, you might want to notice something about the square root of 28. I wouldn't mark it wrong if you didn't do this, but you could take the square root of 28 and you could write that as the square root of 4 times 7, because 28 is 4 times 7. And you are allowed to break up square roots across multiplication. You can't do it across addition, but you could do it across multiplication. And why would I do that? Well, I hope you realize the square root of 4 is just 2, so you get 2 square root of 7. So you could write this as plus or minus 2 square root of 7 times I. We still have that 2 in the denominator. That's nice. These 2's cancel, and you just get square root of 7i. Okay, so in this case, technically, I forgot the plus or minus, didn't I? So you get plus or minus the square root of 7i. Those are our two roots. One root is positive 7i. The other root is negative 7i. Okay, so we call this an example of a purely imaginary root. Okay, because it has this I in it. It's not a real number. This is not a real number. We cannot use this method here. This will not work when you have an imaginary root. This was only for real roots. All right, and I think you might remember, we covered this, I believe, on Tuesday, just yesterday, Wednesday in class. We covered what happens when you get one of these roots. The solution is different than, instead of using E, like we did here, we use sines and cosines. So here's the solution. Hopefully this will look familiar to you. Solution, our function y, or y of t. By the way, sometimes I write y of t just to remind ourselves that y is a function of t. It doesn't mean y times t. It's just I'm writing it that way, like f of x. Okay, y of t would be, Well, it'll be c1 times our first type of function. Our first type of function is a cosine of of this number here. This number here, square root of 7. So square root of 7 times t plus c2 sine of square root of 7 times t. Notice in here, there's no I in here. I just used the square root of 7 to go here and here. That's actually the frequency. Square root of 7 is the frequency in those sine and cosine functions. What do I mean by frequency? Well, you know how a sine curve and a cosine curve, they're just shifted slightly, oscillate like that. When you change the frequency, if I change the frequency, it might look something like this for a shorter frequency. And so that's what changing that number does. Some oscillations will oscillate more quickly than others, and that's what that number controls. Okay, but nevertheless, this is the solution. This right here is the solution to this differential equation from way up here. Okay, that's the solution. All right, so if I had some initial conditions like y of 0 equals 3 and y prime of 0 equals something, then I could plug those initial conditions in and I could solve for C1 and C2. Since I don't have that, this is just called the general solution because it has the C's in it. Okay, so there's one example. We actually did one like that in the last class, Wednesday. All right, let's do another problem that's similar to this one. Let's keep going. All right, so this one will be, how about this? So suppose we have a spring, a spring damper mass system. You might see pictures of stuff like this. You've got a large spring with maybe a damper. You can see this in, like, if you look up at some doors, they have a sort of a damper at the top of the door to prevent it from slamming. Or you can see this underneath a car, like a shock absorber. But in any case, well, suppose that the spring stiffness is say 8. The dampening is 3 and the mass is 1. We won't worry about units. But the way that works out in a differential equation, the mass is always multiplied by the acceleration. The acceleration in a differential equation is the second derivative of y, right? Plus the dampening, the damper, or friction, that's also sometimes just a result of friction, times the velocity, and then the spring stiffness by the spring, some people call that the spring constant, times y equals 0. And why is the right hand 0? Well, the right hand side would not be 0 if you had a function being applied to this device. But for the time being, we'll pretend that that's not happening. That makes it homogeneous. All right, so in this case, what do we say? This is 1, this is 3, and this is 8. So our differential equation is y double prime plus 3y prime plus 8y equals 0. This is our differential equation. This is what we want to solve. If we solve it, it'll tell us, maybe y is like this distance here. Maybe it could be like the distance. The y could be like the distance of your bumper of your car above the ground, for example. And then that, you're measuring how will that change when you hit a bump, and your shock absorbers, do a couple things. This spring prevents it, from extending too far. The dampener will slow down how quickly it moves. The mass will provide some inertia. All right, so let's solve this and see what happens. All right, so the technique, it's the same as always. We create the polynomial. In this case, it'll be r squared plus 3r plus 8 equals 0. You could try to factor this. That's how we typically start out. If it does factor, this will be r and this will be r. And then remember, these two numbers here, whatever they are, they have to multiply to equal 8. So you could try 4 and 2, or you could try 8 and 1. No matter what you try, you'll find that you can't get the middle term to equal 3r. So we failed. It's not going to factor. This one actually doesn't factor. I chose it. It wouldn't factor. So that's okay. We'll just use the quadratic formula. Yeah, make sure you have this memorized. Here it is right here. So in this case, what's a, b, and c? We'll have to use the quadratic formula. And a is 1, b is 3, and c is 8. All right, that shouldn't be too bad. So we get our roots now. Negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 8, because that's 4ac, all over 2 times a. Let's simplify that out. Negative 3 plus or minus, let's work this out. Isn't this 9 minus 32? 4 times 8 is 32, all over 2. All right, so we're going to get negative, let me go down. We're going to get negative 3 plus or minus the square root of 9 minus 32. Right. So let's see, that's negative 23. Because 23 plus 9 is 32. So, and there's more negatives than positive. So it's negative 23. Oh, you can see we're going to get an I here, all over 2. Well, let me show you something. We prefer to write this. We prefer to separate this into two fractions. So we'll write this as negative 3 over 2 plus or minus the square root of negative 23 over 2. All we did was split it up into two fractions. You'll see why in a second. If I pull that negative out, this will be negative 3 over 2 plus or minus square root of positive 23 over 2 times I. Where'd the I come from? We had a square root of negative 23. The square root of negative 23 is the square root of negative 1 times square root of 23, which is just I times the square root of 23. So I just put the I second here. So that's how we got this. I want you to look at this carefully. You see how this first number doesn't have an I into it? We call this the real part this is called a complex number altogether. It's a non-real complex number because it has an I component. That's the real part. The real part is negative 3/2. And this is what we call the imaginary part. We don't want to put the I in our solution. We don't want to write the I as part of our e or sine or cosine functions. What we care about is this number in front. This number in front will be the frequency of an oscillation. That'll be the number that goes inside the sine and cosine. The real part will be this is the coefficient of t in e to the rt. All right, so nevertheless, another way to think about it is every complex number, and you may have seen this maybe in high school or something, you could write a complex number as a plus b times I, where a is the real part and bi is the imaginary part. For some reason, our book likes to be a little fancy, and it instead of using English letters a and b, it uses Greek letters alpha plus beta I, but it's the same thing. So in this problem here, alpha is negative 3/2, and beta is square root of 23 over 2. Right? Because the alpha comes from there and the beta comes from the coefficient of I, whatever's in front of the I. We don't need to worry about the plus or minus here. By the way, every time you get a complex valued root, like we did in this problem, from this polynomial that we were trying to solve, every time you get complex valued roots, they always come in what are called conjugate pairs. That just means the two roots they have the same real part, but their imaginary part changes from plus to minus. It turns out we don't care about the I or the plus or minus. We don't need them in our solution. We do need the coefficient of I. That'll be the frequency in our sine curve. sine and cosine curves. And the alpha we need because that'll be part of an exponential. And I'll show you how to write the solution. So here's the solution to the differential equation. In general, it'll be y, or y of t, is equal to e to the alpha t times, I forgot our c, by the way, I meant to write c1 here, e to the alpha t times cosine of beta t plus c2 e to the alpha t times sine of beta t. So keep in mind, both terms have an e to the alpha t in front of them with the same alpha. You could actually factor that out if you wanted to, and you could write it as e to the alpha t times c1 cosine of beta t plus c2 sine of beta t if you want to. It's the same thing, just factored. Either way, if you'd like to just write e to the alpha t once, but it's so the alpha just goes there, and the beta goes there and there. You see, alpha also goes here. So let's write the solution to the one we just solved. In fact, how about this? I'll zoom out so you can see it again. I'll scroll back up. Now we can write our solution. We've got our roots, right? We always remind ourselves of what the roots are. The question was to solve it, and we now have our solution. Use a different color. Remember, our alpha was -3/2. You do have to include the negative with the alpha. For the beta, you don't really need it. You can just say it was square root of 23/2. Doesn't matter whether that's positive or negative, but the alpha definitely has to be negative. And our solution is y of t, I should start with c1, our arbitrary constant, e to the -3/2 t, because that was the alpha, times cosine of square root of 23/2 t, because that was the beta, plus c2 e to the -3/2 t times sine of square root of 23/2 t. Good, that's the solution. That is the solution to this differential equation. And how did we get it? Well, when we solved this auxiliary polynomial equation using the quadratic formula, we found, how did we get the -3/2? Because that was the real part of our solution for our, how did we get the square root of 23/2? That was the coefficient of the complex part. So that's what went here and here. And the -3/2 went into the exponent of your exponentials. So this is sort of a blend of the two techniques. Remember, when we get real roots, we have exponentials. When we have purely imaginary roots, we get cosines and sines. In this problem, we got some of each. We got a real part and an imaginary part. If you want to know where that comes from, I'll show you real quick. So last time we talked about how e to the I t could be written, or how about this, e to the I, e to the ix could be written as cosine of x plus I sine of x, and then there's a way to get from that when you have, so anytime you have an I in your exponent for e, it actually results in cosines and sines. Well, imagine you had e to the alpha plus beta I times t. Well, I hope you realize we could write this as e to the alpha t plus beta I t, which is e to the alpha t times e to the beta I t. So in other words, whatever we did before with cosines and sines will come from this part, cosine of beta t plus sine of beta t, but it'll be multiplied by the e to the alpha t. That's how it came up. That's why this is the general solution. Again, this is the general solution. If I gave you some initial conditions, you could find C1 and C2. Okay, good. So that's how that works. So, all right, so how about this? I'll give you a summary table of all the different things that can happen when we're doing this. This will summarize everything we've done over the last maybe 2 or 3 lectures. So let's try to summarize it here. And then you should be able to do the worksheet. It's posted on Brightspace. There's a PDF there. So here's a summary. So in all cases, you're solving the differential equation ay double prime plus by prime plus cy equals 0. Okay, so let's talk about this case 1. There's going to be three cases. Case 1, case 2, and case 3. Right, in case 1, when does that happen? We get two different, in other words, roots, two different roots, which are real numbers. Call them R1 and R2. When does that happen, by the way? That happens when in this expression right here, b squared minus 4ac, that's the part underneath the square root of the quadratic formula. When that's greater than 0, this is when that happens. And the solution is, let me write that in a different color. The solution is y equals c1 e to the r1t plus c2 e to the r2t. And that's the solution. That's the first case we did. That was, you probably remember that. All right, let's talk about the second case. That was the second case. I think this is another slightly different case. So instead of getting two different real roots, what if you get the same root twice? Remember, this happens sometimes. Sometimes when we factor our polynomial, we might get something like 2r plus 1 and 2r plus 1 equals 0. So both roots are the same. R1 equals R2. So when that happens, we get a repeated, so we get one root. It's considered a repeated root because it occurs twice in the factorization. One repeated root. If it's a repeated root, it'll be real. So it's real automatically when this happens. Remember, we handled this case the other day. We don't want to just write the same root twice. So here's, by the way, when does this happen? This happens when b squared minus 4ac equals 0. That's when that happens. Because then you don't get the plus or minus part in the quadratic formula. And the solution is, right, different colors so you can see it. The solution is y, or y of t, is equal to c1 e to the r. Let's call this one root r1. So it's c1 e to the r1t plus c2 e to the r1t. Remember, you don't just want to write the same thing twice. The trick was, what we learned the other day, is you put a t in front of it. You put a t in front of one of the two terms. That's a complete solution. That's how you accommodate the fact that these expressions would otherwise be the same if they didn't put a t in front of one of them. All right, so that's when you get only one root. So we've covered the case where you get two different real roots. We have one real root. The third case, that's the one we just covered today. That's when we get complex roots. Alpha r would be alpha plus or minus beta times I. When does that happen, by the way? It happens when b squared minus 4ac is less than 0. Because the ba squared minus 4ac, if it's less than 0, you get a negative underneath that square root sign. You're going to get an I out of that. And that's what we just learned today. What's the solution? Well, I'm running out of colors here. I'll pick something. Okay, here's the solution. I guess we should put the solution here. The solution is y equals, we take that alpha part, and that we start with c1, and then e to the alpha t, and then the beta becomes the frequency and a sine and a cosine, so we'll go cosine of beta t. It really doesn't matter whether you do cosine or sine first, just as long as you get them both, plus, put plus right here, c2 e to the alpha t times sine of beta t. Right, that's really what we did in the last problem. That's the general solution when that happens. Okay, if you get a real part and an imaginary part, the real part becomes part of the E. The imaginary part gives you the frequency inside of a sine and cosine. All right, so Good. So that's all the cases. Now we can spend some time on review on Monday, but you should be able to do the worksheet that's posted on Brightspace. And thanks for joining me.